Start.
Okay,
Start.
so hi everyone. This will be a short session on adversarial machine learning. So let's start with some definitions. So adversarial machine learning by definition is the fooling of a model by giving it some malicious input. So the process of attacking a model is to craft some inputs in such a way that you can fool the model, and there can be two ways majorly that you can attack a particular model. One way is targeted and the other is untargeted. So untargeted attacks are easier because they have more space for optimization, and targeted attacks are not that successful. However, these are more useful because targeted attacks give you more control over the output. So on the other hand, these can also be classified into black box or white box. The black box models assume that you don't have the knowledge of the model's actual specifications, and white box model you have access to its gradients and the model as well. So adversarial machine learning attacks can be made on supervised learning, unsupervised learning, or reinforcement learning as well. Right now, we'll only discuss about supervised methods and white box attacks. So suppose these will be the definition for the rest of the presentation. Suppose we are given a model F and it maps a certain input X to another space Y. Then the definition of my attack would be G, such that it samples another distribution by perturbing it, and the X dash, which should be its result, should be in the same space as well. So the attack is defined to be successful if fx dash is y dash, where y dash is not equals to y. So for a targeted attack, you have a particular mapping for y to y dash. So let's take an example of sentiment analysis. So an untargeted attack would be simply flipping the positive and negative labels if you are talking about binary classification. Whereas a targeted attack could be simply classifying all the positive sentiments as negative or the opposite. So the other important aspect for any adversarial perturbation is how deceptive an attacker is. So for an example, by the previous definition, you could also say that if you like entirely change the class to another class, so it will still work. But there comes the deception or the distance between the training sample and how you constrict your attacker G. So when g x equals to x dash, so you have a particular distance metric which we'll define as psi. So psi x dash less than equal to epsilon. Here we are showing that epsilon is a particular threshold. The perturbation should not be enough that the entire meaning of the original training sample changes. So, for example, if I put a message, "How are you?" This is not a negative sample, but if I add some abusive words to it, it will be a negative sample. So we don't want the perturbation to be such that it crosses a certain threshold. For speech or image, it is slightly easier to calculate these perturbations, whereas in text it is a bit difficult because the actual data is discrete and not continuous. We'll discuss more about why perturbing text data is a little more difficult. So here is an example from the harvesting adversarial attacks. So here you are using "how are you" and adding a small perturbation, and the classifier says it's "open the door." And here, as you can see, the difference between the two images after adding a small noise uh, to us is not so that you can misclassify. However, panda here was being classified as 65%, and adding this small noise changes the classification to gibbon with a 97%. confidence. So now we'll move to adversarial attacks in natural language processing, and we'll talk about white box attacks, particularly hot flip. So representation here is how the input is made. So this paper came out in 2017. This will be necessary because our explanation for the next paper will be heavily dependent on it. So here the jth character of the ith word is represented by xij, where where xij is a one hot vector for the vocabulary. Here the attack is being done on character level only. So v is the set of alphabets that you are using for your input data. So, since the paper is named hot flip, let's discuss what a particular flip is. So, a flip is a vector that can change your input matrix such that it changes one particular character. It can also do the same thing for insertion or deletion. However, for the scope of the actual presentation, we won't need that. So here we'll define what a flip is. So as you can see, -1 and 1 for this particular character in the ij position represent that the character at this position and is being removed, and at this position is being added. If you think of if you realize what the input representation is, that will help you understand that how the vector is actually transforming the input matrix. So yeah, -1 and 1 are corresponding position for the eighth or bth characters of the alphabet, respectively. A first order of so yeah, this is the prime idea for the entire paper. This needs to be understood. So given that the model has the loss function as j, given x and y, so we obtain a first order derivative over here, or a first order derivative approximation to what the perturbation, how the directional derivative is changing the perturbation. So here you can see that this is the directional derivative for the particular vector, and we can approximate it in the first order by Taylor expansion uh, as this, and this particular part can be easily calculated, and this is just a vector manipulation after that. So we take this derivative to optimize the flip. So when the flip gives you the new label, we name it as the hot flip attack. So this is a character flip, and for a word flip, you can also use words instead of characters. In that case, your set of vocabulary won't be alphabets anymore, but it will change to the set of words that you use in your dictionary. A limitation to this is that you need to have a specified maximum length and word, because this will always be a fixed size matrix for calculation. So now we move to universal adversarial triggers. So adversarial examples highlight model vulnerabilities and are useful for evaluation. A problem with hot flip, or in general any other white box attack, is that from the usage point of view, it is not as devastating, because in most cases you won't have the access to the model that is being used. So this paper talks about universal white box attacks. So our objective over here will be obtaining a set of triggers, or a sequence of words which you can use, which will be input agnostic. So you can use it in any data set and for any model, and it will adversarially attack it. So the example over here is, for example, triggers cause SNI entailment accuracy to drop from 89.94 to 0.55%. So, and 72% of why questions in squad to be answered to kill American people, and the GPT-2 language model to spew racist outputs. Even when the training data itself is conditioned on non-racial context, Further, we'll talk about how the triggers are being optimized, and we'll make use of hot flip over there because this paper developed on hot flip only. Let's define what our universal attack would be. So the universal attack in a non-universal targeted attack, we are given a model F, a text input of tokens. The tokens can be words, subwords, or characters. It's up to your choice. Just that you will need the representation in that sample only, and a target label y dash. The adversary claims to concatenate the trigger tokens to the front or end such that you can see that ft this is being used over here for concatenation. Please don't confuse it with the earlier notation. So for the attack to be universal, we aim to search the triggers such that the loss over the complete model is minimal. So this is mathematically defined over here. We are trying to find trigger tokens VADV such that the expected value of the loss after appending these tokens at the end of the entire input gives us the least loss for the target labels. Yes, this is a targeted attack over here. How to convert it into an untargeted attack will also be discussed later on. So yeah, so the main thing about this is how the trigger is being searched. So we initially begin with stop words. Taking from the paper, these three tokens will be taken to as the initial set off. And the problem, yeah, so now we'll talk about why discrete input is difficult to manipulate or make gradient based attacks. So the problem with text permutation is that it's discrete. Therefore, like to obtain the gradient, you cannot optimize it according to your gradient. So instead, there are approaches where brute forces for all the tokens can be used, but for large models or for large data set, this will be very computationally expensive, and this is not what you would ideally want. So the technique that we'll use over here is inspired from hot flip and is similarly based on the linear approximation for the task loss. And then we'll update the embedding for every trigger token E adversarial to minimize the first order Taylor approximation around the current token embedding. So this is a visualization of how the trigger is being updated. So suppose you have the and you append it to the batch according to your position. So this paper explicitly doesn't talk about where you will append your tokens or push, but work has been done around appending these tokens at the beginning of the text or at the end of the text or even at the middle of the text. Due to the discrete nature, it is difficult to optimize the location for the attack, but work is still going on in that area. So here we obtain the gradient for this batch and use it to optimize the next set of tokens. And similarly, till we reach a threshold, we keep optimizing it. So for GPT-2, these three tokens, zoning, tapping, fiends, were used. And as I discussed earlier, so GPT-2 was spewing out racist output when being conditioned on non-racial text. The output was conditioned to be such without training or changing the parameters. So you just need forward passes, and that will make it very computationally efficient because you're not back propagating over here. You're just obtaining the gradient and updating the triggers. How the update is being done, as we'll discuss with the mathematical equation and the particular code that I am using right now. So E adversarial. So our work is to find. So this is the hot flip. This is where the hot flip arrives. So here also we have taken the first order uh, Taylor approximation for the loss task, and this is why we can approximate this as well. So here you can see that we are taking the averaged gradient and we are taking the embedding matrix. Just an update that for better attacks, embeddings will be necessary over here because you need information for tokens that are out of the vocabulary as well. So here we obtained the gradient dot embedding matrix. So here we are doing an Einstein sum over the gradient and the embedding matrix. So as we were discussing earlier, this was the entire paper revolves around targeted attacks, but you can also make it untargeted. So in untargeted attack, as your intuition would go, our strategy should be, instead of taking the minimum of the loss, it should be optimizing to get the maximum loss. So instead we multiply it by -1, and we optimize it for the maximum loss. And then the processes in these cases are not memoryless. So suppose I have a sentence, Ram goes to office, and just so if you take these tokens, these have sequence, these have a syntactical structure, and changing the sequence will entirely change the meaning. So you cannot assume that it is a non-ordered set. It is a sequence, and therefore we augment beam search to optimize the search strategies as well. This is a small example of how beam search would look like. And these are the probabilities. So as you can see over here, the beam search works on the principle that you take a particular beam size, say 5 for this example, and it computes the 5 top values continuously. Uh, so this way, and at the end, you will have your 5 candidates. You will take the conditional probabilities for all your 3 tokens and keep computing the 5 top candidates until you reach the end, and then you will simply take the maximum of them. Uh, yeah, so if anyone has any questions.